So far, and we have this carbonyl carbon that's an amazing electrophile, and we've seen lots of different nucleophiles attack it. We've seen oxygen nucleophiles attack it to create acetals. We've seen primary amines attack it, nitrogen nucleophiles, to create imines. We've seen secondary amines attack it, another nitrogen nucleophile, to create enamines. We've seen sulfur attack it as a nucleophile to create thioacetals, which you can then reduce with Raney nickel. We've seen hydrogen nucleophiles attack it in the form of lithium aluminum hydride and sodium borohydride. And now we can see carbon nucleophiles attack it. Now the mechanism behind all of this is just the same exact thing over and over and over again. These nucleophiles attack the carbonyl carbon. And in this case, we make carbon nucleophiles through a similar process of reasoning as how we made how we made hydrogen nucleophiles. We bond the carbon, which is not by itself very electronegative, to a metal. Now here we're going to be bonding it to a magnesium, which will be stabilized by a bromine, and hopefully you'll recognize this recipe as a Grignard reagent. So Grignard reagent is a pretty classic carbon nucleophile. Here we have an ethyl group in this example, so CH3, CH2, and that's being bonded to a magnesium and a bromine. Now the magnesium by itself, if you remember, magnesium is an ion that normally has a 2+ charge. That's pretty unstable, and bromine is an ion that usually has a -1 charge. Well, you can bring those together, and overall that would only have a +1 charge, which is more stable. So the bromine is there to help stabilize that magnesium. But the magnesium is really far to the left on the periodic table. It's in group 2A. And so really, this bond here, that bond in between the magnesium and the carbon, is really almost an ionic bond. You almost have just an ethyl group with a full lone pair and a negative charge ionically bonded to this magnesium bromide with a positive charge. That's the magnesium bromide altogether that has the positive charge. And so, when you see that magnesium and bromide, you can sort of think of the carbon as its own nucleophile. Well, what's going to happen when we combine a carbonyl with that? In this case, a ketone. And when you see this, remember, try to make associations, remind yourself of the things you learned in previous chapters. Remember that you could make this doing a Friedel-Crafts alkylation. You could have benzene reacted with the acyl chloride and AlCl3, and that would give you that molecule there. So that's just a fun callback. Okay. Well, once we have that, what can we do with it? We can treat it with a carbon nucleophile like this Grignard reagent. Now I'm going to focus on this bottom one, and really it's this carbon there that acts as the nucleophile. We know our carbonyl carbon is very slightly positive because it's losing electron density to the oxygen, which is very negative. So our carbon nucleophile can swoop in and attack the carbonyl carbon. The pi electrons go onto the oxygen, just as we saw in the case of hydrogen nucleophiles. And what we get after that is just one bond to the oxygen. It had 2 lone pairs before, now it has 3 with a full negative charge. And we also have 2 more carbons added, so 1, 2, right? So be careful when you add those on. We have 1, 2 carbons here, 1, 2 that we've added on there. Now we just need to stabilize that positive charge with a proton transfer, and that's why we have the water. Or sorry, stabilize the negative charge with a proton transfer. And so we have this water here, the fully negative oxygen steals one of the slightly positive hydrogens, the electrons snap back onto the oxygen, and you have an alcohol and your carbon chain. So notice that this really gives you the same thing as we got in the case of the hydrogen nucleophiles. The only difference is that instead of a hydrogen, we have a carbon chain, right? In the case of the hydrogen nucleophiles, that carbon chain, that new carbon chain, was just a hydrogen. But in this case, it is whatever the carbon chain is in the Grignard reagent. So when you're drawing the products for Grignard reagents reacting with aldehydes and ketones, turn the carbonyl into an alcohol, and on the carbonyl carbon, add the carbon chain from the Grignard reagent. Okay, let's try that same process with B. So pH, that's standing for phenyl. That's what benzene is called when it's a branch. So that's a pH is a benzene ring. You notice this is the opposite of pH, the measure of acidity. You have a capital H, P, and a lower h, right? When you're talking about the amount of acidity, it's a lowercase p and a capital H. So not that. We're dealing with this pH here, and that's a phenyl. So that's what benzene is called when it's a branch. And here, that is branching off of the magnesium bromide. Now ultimately, this is kind of an ionic bond where the carbon steals the electrons from the metal, becomes slightly negative, and this magnesium bromide altogether has a positive 1 charge. When these enter solution, this kind of sticks around, but isn't like a soccer mom. It's just kind of hovering maybe at a small distance. We can take that nucleophile and combine it with our electrophile, which is the carbonyl carbon. And here we have acetaldehyde. So the carbonyl carbon is slightly positive because it's losing electron density to the oxygen, which is slightly negative. This carbon nucleophile can attack the carbonyl carbon, kick the pi electrons onto the oxygen. That oxygen had 2 lone pairs. Now it's going to have 3. So we have our original benzene ring. We have this 1 carbon with a hydrogen on it, the bond to the oxygen, which now has 3 lone pairs and a full negative charge, and a bond to another benzene ring. This is the benzene ring that we added over here. Well, that's almost stable. We just have to stabilize that negative charge with the proton transfer, and that's why we have water here in the second step. So this fully negative oxygen can steal that slightly positive hydrogen. The electrons snap back on that electronegative oxygen there, and we get our 2 benzene rings with a carbon in between. So that's this, just viewed twisted. And then you have an OH in between there. And so that is what you get. Really, if you compare it with what a hydrogen would do, you have that same structure, but the carbonyl turns into an alcohol. But now, instead of with the hydrogen nucleophile, we had a carbon nucleophile, so we add that on to the carbonyl carbon. And so that is the product that we get with that carbon nucleophile. So I'm going to minimize this stuff just so we have room for C. All right. Now you look at this one and you can start putting some things together. Notice we have an acetal over here, and that really is a carbonyl group in disguise. And now you can see, we talked about how you can control the equilibrium of acetals using Le Chatelier's principle. You can keep this as an acetal for now, do this reaction so it'll only occur at the other ketone, and then add some water to undo this and you'll get the ketone again. So this is a way of protecting one of the ketones with an acetal. So it's kind of a neat thing to notice there. We have phenyl magnesium bromide, so that's the same nucleophile as before. The pH is standing for a benzene ring, acting as a sort of branch, and that's going to be bonded to the magnesium bromide. But the magnesium has a really low electronegativity, so it's basically an ionic bond, not quite, but basically, where the magnesium bromide has a positive charge altogether, and the carbon has a negative charge. So this is sort of floating around, hovering around. And that can act as a nucleophile to attack our electrophilic carbonyl carbon. So in that carbonyl, the carbon has a slight positive charge because it's losing its electron density to the oxygen, which has a slight negative charge. So our nucleophile with a negative charge can swoop in, attack that carbonyl carbon, the pi bond breaks, the electrons go onto that oxygen. It had 2 lone pairs. After this, it's going to have 3. So actually, so we still have the same carbon chain. The oxygen is only attached by 1 bond now. It has 3 lone pairs and a full negative charge. And on the other side, we have this phenyl ring bonded, the benzene ring. So we have that there. We just have to stabilize this negative charge with a proton transfer, and that's why they're giving us hydronium there. The H3O+, that's a source of protons, source of H pluses. So the fully negative oxygen can steal one of these slightly positive hydrogens. The electrons go back onto the oxygen of the hydronium. And what we end up with there is the same structure, but that oxygen, instead of having a lone pair with a negative charge, has a hydrogen bonded to it. And normally I've just been writing that as an OH. So it's very similar to our original structure. If you compare it, we have the carbon chain that's exactly the same. The ketone has turned into an alcohol, and we've added our carbon nucleophile onto the carbonyl carbon. Okay, so that's what you do. Those are the products you get when you have a Grignard reagent reacting with aldehydes and ketones. They turn the aldehydes and ketones into alcohols, and they add themselves onto the carbonyl carbon. And the mechanism is really the same as we saw for the mechanism for the hydrogen nucleophiles.